Hi everybody. So in this video, I'm going to show you how we can apply Pythagoras' theorem to 3D shapes. So we'll work through a couple of examples and then we'll try some exam style questions. And if you want to work along with me, you can download this PDF from my website. I'll leave a link below. So in example 1, we've been given this cuboid and we need to begin by finding the length e to g, which is this length here. So whenever you want to work out a length in a solid shape, using Pythagoras' theorem, we need to identify a right-angled triangle. So in this case, the right angle, which e to g is a part of, will be EFG, and our right angle will be at point F. So if we sketch this out, we know the length from F to E will be the same as from A to B. So this will be 11 centimeters. So we'll mark this on the diagram. And then from F to G, this will be the same as B to C, which is 15 centimeters. So to work out E to G, using Pythagoras' theorem, the area of a square on this side will be 11 centimeters squared. The area of a square on F to G will be 15 centimeters squared. And these will add together to make the area of a square on E to G. So to work out E to G, we'll square root both sides and we'll get the square root of 15 squared plus 11 squared. And this works out as 18.6 centimeters. So I'll label this on a diagram. So that's E to G. Then for part B, to work out A to E, we need another right angle triangle, which you can see is given in this red dashed line. And the right angle is at G. So if we sketch out this triangle, we've got G as our right angle. We know G to A, the height, will be the same as E to C. And this will be 21 centimeters. And this horizontal length, G to E, we've just worked out as the hypotenuse of our green triangle. So we can label this as 18.6. Then applying Pythagoras' theorem again, we can work out the hypotenuse of our red triangle. This will be the 18.6 squared plus the 21 squared to make A to E squared. Okay? So then A to E will be the square root of 18.6 squared plus the 21 squared. And when we work this out, we get 27.65 centimeters. Okay? So it's all about identifying right angled triangles and then going from one clue to the next. So we had to work out E to G, and this allowed us to work out A to E. Let's try example 2. So for example 2, we've been given this blue cuboid, and we need to work out the length B to G, which is this length here. Can you identify which two other sides would give us this as a right angled triangle? So this would be B to D and then D to G. Our right angle would be at D. So what I'm going to do is sketch this out separately as a 2D shape. We have a right angle at D, and we know the height is from D to G, and this is the same as the 9 centimeters. The problem we have is that we don't know this length, D to B. If we did know this length, we could use Pythagoras' theorem to work out G to B. So what we need to do is identify another triangle where we can work out B to D. Can you see which triangle that might be? So I'm going to go from B to A to D. Now our right angle will be at A. So if I sketch this one out, the right angle's at A, and then A to D will be the same as B to C. So this will be 4. And then from A to B, we've got 15. So we can work out d to b using Pythagoras theorem. This will be bd squared. This will equal b4 squared plus b15 squared. So we can work out bd. We'll take the square root of both sides. And 4 squared is 16, 15 squared is 225. So this will be the square root of 241. So we could work this out as a decimal, but we're going to square this when we apply Pythagoras' theorem to this triangle. So it's easier to leave this in square root form. So I'll label this as root 241, and we'll do the same for the red triangle. Notice how it's the hypotenuse in our purple triangle, but the base in our red triangle. That's why we need to draw two separate triangles. So we can work out g to b then. This will be the 9 squared plus the root 241 squared. And when you square the square root, these will cancel. So GB will be the square root of 9 squared, 81, plus the 241. And when you work this out, we get approximately 17.94 centimeters. So this will be the length of G to B. Okay? Let's try example 3. So in example 3, we need to work out the height of this rectangular base pyramid. This is the length E to F. So perhaps you want to give this question a go yourself. Begin by trying to identify the right-angled triangle that this is a part of, and then take it from there. You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So the right-angled triangle would be from E to F, and then from F to the midpoint of a line C to B. And the hypotenuse of this triangle would go from E to that point. And I'm going to call this point M. I'll label this here. So it's a good idea now to sketch this triangle separately, when this is the right angle. So we have the right angle at point F, and if this is the center of a rectangle, then from F to M will be the half length of A to B. So this will be 6 centimeters. The problem is we don't know the length E to M. So I'll label this point as E. What we need to do now is to find this length using another right angle triangle. If we identify that as E to C, and then from C to M, and E to M, our right angle will be at M, which is here. So if this is point M, we know C to M will be half of this length, so this will be 5. We know the perpendicular height is from M to E. This is what we're trying to find out. This will give us this length. And the hypotenuse is from E to C, and we're given that as 14 centimeters. So using Pythagoras' theorem, E to M squared will be the 14 squared minus the 5 squared. So we'll take the square root of both sides, and E to M will be the square root of 171. And because this is going to go to this length, which I'm going to have to square, I'll leave this in the square root form. So I'll leave it as root 171, and we'll also include it on our blue triangle as well. So now we can work out the length E to F, which is the height of this pyramid. This will be E to F. It'll be the square of a hypotenuse minus the 6 squared, or minus 36. So E to F will be the square root. These two will cancel. So we'll have 171 minus a 36. And this works out as approximately 11.62 centimeters. Okay? Let's try example 4. So here we've got an exam style question where we need to work out the volume of this cuboid. We're given a to b is 7, b to d is 5, and b to g is 15. Do you want to give this question a go? You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So we know the volume of a cuboid will be the area of the cross-section. I'll choose this rectangle as my cross-section. This will be the 5 times the 7, so 35 centimeters squared, multiplied by the depth in centimeters. And the depth would be any of these 4 lengths, okay? So I'm going to take this as the length A to E. If I work this out, I've got the depth, and then I can work out the volume. And I can work out A to E as a right-angled triangle shown in blue, when this is the right angle. So we've got our right angle at A to B, we know is 7 centimeters, but we don't know A to E, and we don't know B to E. So we need to work out one of these lengths using another right angle triangle. And we can do this with G to E to B, because we've been given that hypotenuse. So E to B, we don't know. We know the hypotenuse is 15, and we know the height is 5. This length is the same as this one. So E to B squared will be the 15 squared minus the 5 squared. We can work this out and we get 200. So E to B will be the square root of 200. And again, because I'm going to square this when I put it here, I'll leave it in square root form. So we've got root 200 on both diagrams. So A to E will be the square root of the 200 squared minus the 7 squared. This is the square root of 151, which is approximately 12.29 centimeters. Now we can work out the volume. If I just move this down, we'll substitute this 12.29 back into the depth. So the volume will be 35 multiplied by the 12.29, and this gives us a volume of 430.15 centimeters cubed. How did you get on with that? Let's try one final question. So example 5 is a bit more challenging. We've got this triangular prism, and we're told that A to C is the same as E to C. So this is an isosceles triangle. And M is the midpoint of C to D. We need to calculate the length E to M, which is this length. So do you want to give this question a go? You can pause the video and come back when you're ready. So how did you get on with that? If we draw a line from E to M and make this part of a right angle triangle, we'll draw a vertical line down from M and a line from E to that point, and we'll call this point X. This is where our right angle is. Now I'll sketch this triangle out separately. The problem that we have is that we don't know any of these lengths, but we can see that E to X will be half of E to B. So if we create this triangle, EBA, the right angle will be at A. We'll work out this length, and then we'll divide it by 2, and this will give us E to X. So A to E, we're told is 8 centimeters, and then from A to B, we're told is 20. So E to B will be the 20 squared plus the 8 squared, which is 464. So we'll take the square root of that, and we get approximately 21.54. And then if we divide this by 2, we'll get the length of E to X. and this is 10.77. And then for n to x, this is this length, but this is the same as this right angled triangle. I'll label this point y. We know y to b will be half of a to e. So this will be 4 centimeters. And we've got d to b as 17. So d to y will be the square root of the 17 squared minus the 4 squared. And this gives us approximately 16.52 centimeters. And we can label that on our purple triangle. Okay, so now we can work out m to e. This will be the square root of the 16.52 squared plus the 10.77 squared. And when we work this out, we get approximately 19.72 centimeters. Okay, so that's the length of e to m. Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.